I'm excited about this next session, the crop production, basically advanced technologies in crop production, really bringing in a phenomenal group of speakers with breadth of expertise in their regions. After Jeff, we're going to get a really solid dose of some Southeast voices coming in. But I want to first bring up our first speaker, Jeff Basara, Dr. Basara. He is the man when it comes to forecasting and all, and I love listening to him speak, and so I was excited when he's available for this. So, Jeff, the floor is yours.
All right. Thank you for the introduction, Brian. Appreciate it. I heard something about cowboys. Yeah, it's surprising they let me in the enemy territory, right? But it's a pleasure to be here, and some of you might be asking, why is somebody from the University of Oklahoma who is in the School of Meteorology, I'm also in the School of Civil Engineering and Environmental Science, here to talk about these types of topics? And the answer is because weather affects everyone. Climate affects everyone. And particularly when we get into agriculture, weather and climate affect agriculture. I think that that's a known in terms of the big picture of life. And so my particular role at the University of Oklahoma in the School of Meteorology is I work on extremes of precipitation specifically. And so I spend a lot of time working on drought. I also spend a lot of time working on when it rains too much. And also other extremes, heat, cold, all those interactions, and all of them affect agriculture. So I spend a lot of time also working with folks here at OSU, at KSU, USDA, the Grazing Lands Research Laboratory, other agencies across the US and around the world to try and deal with this whole issue of weather, climate, the variability between the two of them, and the important impacts that it has on agriculture. So that's why I'm here today, and I'm here to, and Brian said that I could just be me and just take as much time as I wanted to today, but I'm going to try to keep this relatively short. So let's just think about this for a second. And I think sometimes you know this as much or more than I do. And by the way, I like visiting with folks, especially on the agricultural side, producers, because it helps me to shape my research a little bit more about how we tackle some of these problems. So, I think there's an important aspect of that feedback that's necessary. I'm going to apply when we talk about weather and climate and the challenges between the two, I'm going to apply the former logic of Secretary of Defense Donald Rumsfeld. When asked one time about threats, he said, there are known knowns. These are the things we know. There are known unknowns. These are the things we know we don't know. And then there are unknown unknowns, and these are the things that we don't even know we don't know, right? So let's talk about this from a weather and climate standpoint, what that means, because there are threats, there are challenges, and there are risks. So if you live in this area, you know what the known knowns are for the most part, right? We talk about severe weather, and by the way, if you really want to make a lot of meteorologists upset, especially down in Norman, just tell them that tornadoes are overrated, right? I actually do that all the time. It's great. Why? Because I think features like drought and extreme flooding have much greater impacts than an isolated tornado, even a very devastating one. It's much easier to devastate half a country, like we've seen this year with a drought, than it is with a tornado, right? So tornadoes, to me, are overrated, but they are very popular around here, and there's nothing that'll make the TV meteorologists take their tie off real quick than the fact that we're going to have a severe weather day. But of course, drought and oppressive heat, wildfires, and all three of those things are interrelated, are really important, especially in this region, as well as excessive rainfall, flash flooding. These are all the known knowns. Severe winter storms, we know that. All we got to do is really go back to February 2021. That was pretty fun for those of you who are here. And sometimes we even get intense tropical cyclones that move through the region and sometimes even re-intensify and produce a lot of rainfall. So, the classic pictures, this is what it looks like, right? These are the known knowns. These are the challenges that we have to deal with here in this region, and from weather, and it's inherent as part of the climate as well. And so, we're coming up on winter, ice storms. By the way, there's nothing that will make Oklahomans make a run on Brahms and Walmart and every grocery store in town than a 3-day forecast of an ice storm, right? I mean, it's just going to happen, and their impacts are large, right? They can be some of the more devastating. That, by the way, this picture is from downtown Kingfisher, just down the road. That's not how much water is supposed to be there, right? That's a problem when it happens. And so we see all of these types of interactions happening. And part of that is not just the weather, it's the climate. The climate of this region is actually dynamically unique when we look at it from around the world in a global perspective. And part of it is the image on the left is sort of the climatology of rainfall for the US. And what's fascinating, and it's fascinating to me, is that when we look at that difference as we go from, say, the eastern part of the region to the western part of the region, the Great Plains, we could narrow it down to the southern Great Plains. But when we basically go from, say, central Arkansas to the Oklahoma and Texas Panhandle before you get to the Rockies, we make a massive transition in annual rainfall on the order of, say, from 50 inches or more to sometimes less than 10. And that is a tremendous difference from one side to the other. Now, we see this sometimes when we have complex terrain, like the mountains of the West. We can get these real big differences, but that's simply driven by the terrain itself. The Great Plains has a terrain difference from one side to the other of less than 1%. And so this gradient in precipitation that exists across the Great Plains is actually very unique in the world. We don't see many of these types of features in the absence of terrain. It's one of the reasons why this region is so dynamic from the perspective of climate. The other thing is it's warmer in the south, it's cooler in the north on average. So with that gradient of precipitation east-west and the temperature gradient north-south, it creates some really interesting features and patterns that can exist on a year-to-year basis or even below that, but certainly within the overall climate. So we have a dynamic climate. And sometimes this is called a battleground state from a weather and climate standpoint, because it always seems that the weather and climate are sort of going back and forth. And to be quite honest, we don't exist at normal very often. This is a plot that many of you may have seen, maybe you haven't. This is sort of the annual rainfall for the state of Oklahoma. And each one of those dots represents the average precipitation for the entire state over a given year. We actually have pretty good rainfall records going back to the late 1800s, so we can kind of track this over the course of not only years, but decades and even now centuries. And what's interesting is when you look at that, there's a lot of variability, right? And so we apply sometimes a simple filter there to kind of highlight features and trends. And so those brown areas, there is a laser pointer, fantastic. The brown areas are periods of below normal. So this would be your average for the state, this line. So anything that's below that in these brown areas, that would be drought or extended drought periods. And then actually there are these periods that are above, right? And so bring in the big red arrows. They're the ones pointing to all those drought features. Historically, we know that there are significant droughts of record going back to the 1930s. It was an important drought. For the length of the decade, about 20% below normal precipitation, which over about a 10-year window, that had obviously significant impacts. Years like 1934, 1936, really impactful years, not just in the Great Plains and here in Oklahoma, but actually across the country. 1936, I don't know if there's anybody here that was around then, but it was bad, and I would not have wanted to live anywhere in the US during that window of time. What's also interesting is the 1950s. Actually, the 1950s were probably a more harsh environment in this region. Over the course of about 6 to 7 years, only got about 60% of the annual average rainfall. And specifically 1956 was really bad and really hot, especially in this region. More localized to the southern portion of the Great Plains, but really bad. But then what's also interesting in this region, and it's interesting, we haven't had many of these. We've had a couple little more blips, but nothing quite like what we've had in the past across the state. And then we've also had these areas that are green. And these are non-drought periods, and we call them pluvials. Now, it's an important word, not used very often, but it's an important word in climatology. A pluvial, all floods are pluvials, meaning in a period of excessive rainfall. But not all pluvials are floods. meaning they can be very, very, very important in restoring the water resources of a region, whether that's the soil moisture, that could be surface water, that could even mean groundwater. They're very important periods. And so what's interesting between the 1930s and the 1950s is there was the pluvial, in fact, a great pluvial, the 1940s. How come nobody ever talks about the 1940s? Actually, I ask this question a lot. I have a couple of theories. One is because pluvials are underrated, and droughts are overrated sometimes. But the other part is there was a global conflict going on in the 1940s that kind of had everybody else's attention. But the 1930s and 1950s were really bad. In fact, the largest mass migration of human beings in the last century in in North America was because of the drought of the 1930s. We know people moved around a lot, right? And then a lot came back in the 1940s. We actually had flooding. Most of our flood control devices across the U.S. that were installed by the USDA and the National Soil Conservation Service and others were actually built in the 1940s and in the 1950s. Why? Because all the rainfall they got in the 40s. So it's an interesting place and an interesting dynamic. And more recently, we've had some pretty substantial pluvial periods. And you may say, well, we haven't gotten a lot of rain. Actually, at times we have. And that's one of the main challenges is perception sometimes too. In fact, this one concerns me most because we grew an entire generation of people that got used to having this much water in this region. And we built our infrastructure around this having this much water. And so what happens when we have one of these? Okay, sometimes they call me Dr. Doom and Dr. Gloom at OU, right? But that's some of the big questions. So that's all part of the known knowns and known unknowns, right? And we can go into the known knowns, and we see the iconic images. You know, these images promote thought and depth, and we certainly don't want to see anything that's quite like this. And certainly in the 1950s, we didn't as bad because of some of the choices we make and made in the region, and that's good. But we also know that when we think about something like drought is ever present. This is actually a 4-year window that's a little bit closer to our timeline, going from 2011 to 2014. And what's interesting is we just take drought images from the drought monitor and put them up here at regular intervals. We see that drought was ever present, especially even in the southern Great Plains. It basically peaked, and then it certainly in 2011, if you were here, that wasn't very fun, right? Very hot, very dry, centered mainly over the southern Great Plains. It actually kind of waned a little bit, so drought intensifies, drought weakens and wanes, and then comes back with a vengeance in the summer of 2012 across especially the Corn Belt and the Midwest, extending down into the southern Great Plains. And then it kind of shifts a little bit, and we see the rise of the great California drought of 2015 that begins to emerge in late 2014. But basically, drought is almost always ever present in this region, and it's a major challenge. And we start to see this oscillation between one extreme and the other when it comes to rainfall. And if you don't take anything else away from me today, just remember one thing about the weather and the climate of Oklahoma. Nothing is normal. It's always a little wonky, right? So part of our known knowns is that there's a lot of this variability. We can get these decadal variability, these extreme events like the Dust Bowl or like the Great Pluvial of the 1940s. The other part is that we can have some of these that are a little bit more on the interannual, like 2011, 2012, and then some really amazing years. If you go back and look at some of those plots, 2015, by the way, is the wettest year on record in the state of Oklahoma. 2019 was very wet. 2013 was wet. 2007 was wet. By the way, I like to use this statistic. In Oklahoma City, there's only been 4 times in Oklahoma City where the rainfall has reached 50 inches or more. The first was in 1908, in the record that we have going back in the late 1800s. The first time was in 1908, which I'm originally from Chicago, and I'm a Cubs fan, and that used to be a really important year because that had been the last time the Cubs had won the World Series prior to 2016. They went over 100 years for doing it, right? But the first time was in 1908. What was the second time? It was 2007. So in 99 years in Oklahoma City between 50-inch rainfall tallies. And then it hit it again in 2013, and then it hit it again in 2015, and then it almost got there in 2019, right? So we have, in this region, started to see some of these not necessarily decadal features, but features that are happening at a much higher frequency where we are going back and forth between these extremes. By the way, this year, not going to be great on the rainfall side, right? Because we're on the drought side. So we kind of oscillate back and forth. And we can have back-to-back years of drought and then some of these really excessive rainfall years. And then we call these dipoles because they transition back and forth. And the important thing about those excessive precipitation years, they're not always great, but they do restore some of the water resources of the region, right? But they can have some real important and side impacts on agriculture. This is actually 2015. I spend a lot of time in places like this, outside my office, which is good. This is actually it depends on the time of year. In the top image, it's probably about a 2-acre lake or pond, or however you want to describe it. And the one below is about 8 acres, right? And they're separated, these two images are separated by just a couple of months. And that's the importance of an excessive rainfall event like 2015, is that literally at this location, we got about 2 feet of rain during the month of May. And that restored the water resources. Now, if you also look, the top is drought, everything is dry. I know it's the end of the growing season, but it's really kind of a very sad existence for that ecosystem. But the bottom is actually, if you ever wanted to see an ecosystem that looked happy, that's what it looks like, right? Very green, very lush, responding to the precipitation. But look at the water quality. It's not very good, right? Because we get all this excessive rainfall, we get the runoff. So this is some of the challenges that we have from a weather climate standpoint in the region, is we often oscillate between these two. I know I will get to the outlook, I promise. I'll talk about what's coming. But I also like talking about what's happened. And part of that is we get all this excessive rainfall. And this is actually from 2015. Large portions of the state of Oklahoma and the whole region, but especially over southern southeast Oklahoma, that had over 20 inches more rainfall than they would normally have. And so we get these periods that are really, really important, as well as some of the dry periods. Now, one of the big questions I always get when I talk to people from the agricultural sector is they just want to know one thing. What are the weather conditions going to be like 3 and 6 months from now, right? Today is important, tomorrow is important, we know that. But if you all are hedging your bets and trying to figure out what you're going to do in the next few months, this is the question you want to know, right? So I used to get this question all the time. Now I just throw it into my presentations. One of the big challenges is that this is not a weather issue as much as it's what we call a sub-seasonal to seasonal issue. Right? Because we're not looking from a weather standpoint is basically what happens in the next couple of days, maybe the next week or two. This is getting beyond that timeline into another region of this, basically this continuum between weather and climate. So climate is what the sort of, is your personality. It's the personality of who you are. Like you can kind of think of climate as your personality. Weather is your mood. If you ever notice, you can have different moods, but you always kind of go back to your personality at some point. And in between those two, you can go back and forth, and that's where we are in this sort of area of sub-seasonal to seasonal. So why is that important? Well, let me be really honest with you all. This is where we are not good. And there's a lot of reasons for this. Well, when we want to try to forecast or understand what's happening in this domain, meaning sort of 2 weeks, 3 weeks, out to 6 months, we actually have much more limited skill than we do at, say, 0 to 5 days. Or even if we wanted to try to understand long-term climate. We actually are better at that and short-term forecasts than we are here in this window. And part of the reason is because of the controlling factors. So our ability to forecast weather actually ends at about 20 days. And you might say, well, why? Why is that the case? Because the weather is actually something that's transient. It's constantly moving, and there's high levels of predictability, or there's levels of predictability, but also levels of unpredictability and uncertainty. But like most things, like personality, you sort of tend to go back to the underlying features that are causing that. And what ends up happening is our skill in weather actually goes, when we look at sub-seasonal forecasts, our sub-seasonal forecasts are kind of determined partially by oceans, things that are half a world away, and also by the local conditions. And then when we really go out to longer scales, that's where we got to get into the oceans. But when we get into this subseasonal to seasonal, both the atmosphere, the land surface, and the oceans can all have an impact on what happens during that window. So at a short window, it's really just atmospheric controls. When we get out into the extended, things that literally happen half a world away have a significant impact on what happens to our weather and climate here. So that poses a really big challenge. And the good news, I guess, is we are in that gap between weather and climate, but we're also trying to address this. And so there's a project that actually involves folks at OU, folks at OSU, folks at some of our other regional campuses around to try to address these issues. And of course, have impacts on ecosystems and agriculture as well. So there's actually a lot of ongoing work, but some of the questions we're trying to understand. If we have a drought like what's happening right now here in Oklahoma, has that been forced by processes that are local, meaning the evaporation and soil moisture? Is that something that's being driven by oceans out in the middle of the Pacific, like ENSO, La Nina, or El Nino, La Nina? Or is it just some intrinsic variability in the atmosphere that is something else? Those are really big questions that we're trying to tackle. So, we can go back in time. This is not current, by the way. I looked at this morning's, and because the new drought monitor came out this morning. This is not current. But we can go back in time and kind of use these as examples. I like to show this one because this is basically when we had about as little drought as we've ever had across the United States. This is 2019, which was a pretty wet year, not only here in the U.S., but around, not only in Oklahoma, but around the U.S. And this is what, if we're talking about crops, this is what happens, right? You can actually have too much rainfall. And in places across the region, across the Midwest, there was a little bit too much rainfall, and that created some major problems in the region. Well, how do you end up like this? Have you ever really thought about it? This was a rainfall event that happened day after day after day after day. How do you end up with something like this? And that's inherently a good question. And if you look at the precipitation here, Oklahoma, Kansas, Texas, Arkansas, Missouri, that's over 20 inches of above normal annual rainfall across a huge area. How do you end up with something like this? Right? And why can't we have that now? It's probably the better question. That's a good question. Part of it, we have to understand the science. What are the controls? And believe it or not, what happened in this year was actually something that happened out in the middle of the Pacific. And it's a type of El Nino. It's not even the more traditional El Nino, where the maximum sea surface temperatures, in terms of the anomalies, in terms of where it's warmer than normal, occurred south of Hawaii. And we've looked at all these events. 2015 is another really good example of this. Our wettest year on record looked a lot like this. What does that do? It changes the whole atmospheric circulation and the jet pattern, which then creates basically a series of just cyclones and waves that come out of the southwest portion of the U.S. They draw moisture from the eastern Pacific and the Gulf of Mexico. We get an enhanced moisture flux, and we end up with excessive rainfall in the southern Great Plains. So here's actually something we need to know. If you want to see, are we expecting excessive rainfall in the upcoming year? Believe it or not, this is where we look, in the middle of the Pacific, because it has such an important driver in terms of the entire atmospheric circulation that creates an environment that will produce rainfall here. All right? Okay, so hopefully I've convinced you that that's a little bit important. The other things are local conditions can also impact flash drought. So what is flash drought? That's rapid development of drought. A really good example, believe it or not, was in July of 2012. And this is actually a picture taken just down the road at Marina on OSU property from a camera that we have installed there. Yes, I actually do have, I work there. By the way, whenever I go to the site, I wear my OU shirt. It's great. But this is what it looked like on July 1st. When there was about normal precipitation, and then it stopped raining for 30 days, and that's what it looked like 30 days later. And we saw rapid desiccation of the land surface in that region, and as the whole central part of the U.S. went into drought and flash drought. Are there impacts of that? You bet. This is what it looked like on a regional scale in terms of the great central U.S. drought of 2012. That site is here in Marina, and early in the year did not have drought, and then went into exceptional drought by the end of the summertime. And then, we learned from that, but that's not the only time we've seen these, right? If we go to this year, we've had flash drought again. This is actually from the drought monitor, showing that across, basically this summer, we saw rapid desiccation happen again in this region, really impactful. One of the things that we're doing in my group right now is trying to forecast and monitor these features. So this is actually some of the work that we're trying to do in order to provide better guidance of when flash drought is coming. But this is something that happens on a real, locally driven, it's a known, but also a known unknown how it happens, locally driven, but yet very impactful in the region. And then it can transition into much longer term features. But this was pretty fast in how it developed in here in this region, right? So some final thoughts on this. You know, we're in this issue of known knowns and known unknowns. And we're trying to get to a better understanding of transitioning, especially in the subseasonal to seasonal. What are the priorities in getting this into some of these known knowns? I think we're making a lot of progress. By the way, investment in this country into long-term climate and short-term weather has been much higher than in this gap in between. And so that's another just really simple reason why we don't do well from a forecast standpoint in this region. The problem with that is when we look at this group of people, that's where the biggest impacts tend to be. And so we're trying to fill that gap here locally, but also nationally, trying to get a better understanding of the processes. We want to understand when it's going to rain 3 to 6 months in the future, especially in this region. We want to know when it's going to be dry, believe it. And so, and we're increasing our predictive skill every day, but there's still a lot of challenges. And then, you know, there are actually a lot of unknown unknowns. We don't even know we have questions. Like this whole subseasonal to seasonal thing, 20 years ago, we hadn't even asked those questions, but now they're known unknowns. But there are things we still haven't even asked questions about yet that probably will come to light here in the future. So let's make a small transition. That's just a little bit of background in terms of our fun weather and climate in this region. As Paul Harvey would say, and now the rest of the story, right? So let's go back to our friend, who, by the way, there's always an app for that. And standing in a wheat field and wondering, again, what will the conditions be like 3 to 6 months from now? What do I do, right? This is the main question. Again, though, this is a subseasonal to seasonal issue. So in terms of forecasts, we kind of need to look into the subseasonal to seasonal. And so there are a variety of tools. Now, I showed you that if you want it to rain here in this region, you need really warm temperatures in the middle of the Central Pacific. So what's going on right now? Not that, which means not good, right? And we've seen this now. This is what we call a La Nina signal, and this is current. And it's been very cool in terms of the sea surface temperatures in that region. And it's important to understand what happens in the oceans. The atmosphere is right over the top of that. And so it essentially communicates information to the atmosphere, changes the entire atmospheric circulation when we see these really, really strong signals like what's happening out in the middle of the Central Pacific. So we are in a La Nina pattern, which is not great. Not only are we in a La Nina pattern, but we are in a very rare triple dip La Nina pattern, meaning we've had La Nina now what's going into our third winter in a row. And when we have some of these, if you just look on the timeline, here are some of these triple dip La Ninas, early 2000s. Oh, by the way, the 1950s, we talked about that a while ago. You know, some of these windows where we have these long La Nina periods end up being very correlated in this region with drought. And so going into another La Nina pattern, and we are in La Nina, staying in La Nina, and having a third year of it is not good because they tend to be pretty harsh in terms of overall drought development, not just here, but actually across the U.S. And again, the reason is because La Nina affects the entire overall general circulation of the atmosphere. And what's interesting about it is it produces an environment that basically is just drier in general. It locks most of the cold air up in Canada, and it generally tends to be warmer. And believe it or not, we are actually running above normal in terms of our temperatures again. It doesn't feel like it because it feels a little chilly out there, but compared to normal, we've been running a pretty warm December. Not like last December, which was ridiculously warm, right? By the way, lots of impacts from that. You can have a really warm December, which has a lot of problems, and I would love to hear how your all's agricultural practices changed in the spring because of a really warm December. If you have any time, I'd love to hear it. But we end up being on this border between warm and cool. The cold air tends to get locked up, but every once in a while it makes an intrusion still down into the southern Great Plains. And so that's what we saw in February of 2021. It was generally warmer with a real major cold air outbreak in the middle. And so that's important in terms of thinking about what's going to happen here in the next couple of weeks as well. But generally, it produces a dry, what it definitely does is produce a dry environment, except in places like the Pacific Northwest and sometimes in the Ohio River Valley. What's important about this, and this is sort of hot off the press, is what we think is going to happen, which, by the way, this is kind of what we thought was going to happen last year, and we were wrong. So take this as a grain of salt. But we are currently in La Nina. This is November, December, January. So looking out into the future from a forecast perspective, La Nina tends to hang around, but there's growing thoughts that we might actually end up seeing a weaker La Nina and end up somewhere in between La Nina and El Nino, meaning it's generally what we call neutral conditions, which means that the oceans actually aren't playing a huge role in our local weather. It's very important in El Nino or La Nina, but when it's neutral, other things happen. In fact, the red line here is El Nino, and the growing chance that we'll see an El Nino at the end of the summer is increasing. But this is actually what we thought was going to happen last year, and it didn't, right? We stayed in La Nina conditions. There's always a chance of it staying in La Nina conditions. So, but there is hope that maybe we'll see a weakening of the La Nina as we go into the springtime. But it's still going to be here for a while, and it's still going to have impacts on this region. And El Nino and La Nina tend to have their biggest impacts in the wintertime. And so we're going to see persistent La Nina conditions that are going to drive our weather and climate in this region for the foreseeable future. So that's kind of the good news. Maybe, hopefully, we'll start seeing something that looks a little bit more like this as we go, because this does produce more precipitation in the Great Plains. One of the other challenges, though, is if we go and it's neutral, then that means the local conditions tend to be really important in driving what happens as we go, especially go through the summer. And if we go into the summer dry, guess what the local conditions will likely reinforce? Dry. So even if it goes to neutral conditions, it doesn't mean we're out of the woods yet. So just some thoughts. This is not the current drought monitor. The current drought monitor just dropped, but when I was finalizing my presentation, it wasn't ready. I looked at the most recent drought monitor. It looks very similar to this. This is actually amazing and impressive, because in my years, and I spent a lot of times looking at maps of drought, I'm not sure I've seen one. This is maybe 1936, maybe 1988 in terms of expansiveness of drought across the lower 48. This is amazing in terms of, it's about 80, I think it's about 82% of the US is either abnormally dry or in drought right now in the lower 48. That's a tremendously high number. Very different from what we saw in 2019, obviously. So it's not just us, it's all over the place. And there are pockets where there's been some recovery, and we've even had some rain here, but it has not necessarily had a huge impact on the overall drought conditions. And the way I'm going to show that is, let's look at Stillwater. So the blue curve is what the normal precipitation should be. This is from our Mesonet plot. Mesonet site's just down the road, right here in Stillwater. The red line is actually, the OU red line, by the way, is actually the accumulated values. By the way, that was a joke. You can laugh, right? There's the OU red line here is basically that we are actually above normal here in Stillwater until early June. And then it just kind of, long persistent periods of no rainfall. To the point, and yes, we have gotten a little bit of rainfall, but we're still running here, right here about 6 inches below normal. So we're still in drought, even though it's rained a little bit in the last couple of weeks. Does this rain help? Absolutely. Are we out of drought? No, right? So it's going to take a while to catch up. And this is actually good news, because this is actually a place I spend a lot of my time in, as much as possible this time of year. This is down in Tishmingo, south central Oklahoma. And the reason we are like, why does he care about Tishmingo in the water? Because I like to fish the Blue River, right? And, it's nice to have water in the Blue River, even though it's spring fed. It's nice to have a little bit of rainfall that help. But Tishmingo has been below normal the entire year and then had these really long windows. And right now, Tishmingo is running about 13 inches below normal, right? So we are not out of the woods yet in terms of rainfall for the region. So we're still in drought. What's the outlook? Not good. Persistence of drought. Maybe some La Nina's effects are rainfall in the Pacific Northwest and the Ohio Valley. It's one reason why they're more optimistic that we might see some recovery in those regions. But if you look at the Great Plains, the forecast is for it to not change, to remain in drought as we go forward. How about short term? This is actually, I think, really important. 6 to 10 day outlooks, 8 to 14 day outlooks. You've probably already started to hear this. Yes, winter's coming, and it looks like it's going to come in a harsh way. Maybe not as bad as 2021, but we're likely to see a significant cold air outbreak across the central part of the U.S. going into the next couple of weeks. There's a chance we might have a white Christmas here. It certainly will be cold enough, and we might even get some snow. My wife, her cousin is a producer in Northeast Oklahoma, and this is actually what he said he didn't want to see when I talked to him at our little Christmas party, family Christmas party a week ago. Why? Because with the water levels of all the stock ponds being low, and he runs cattle, he's really concerned that, first of all, the water is out in the middle, and there's all that mud in the middle, and to get to the water, it's going to be a problem. But then if it kind of partially freezes, that produces a lot more problems for him. He's actually very concerned, and obviously doesn't want to see full freeze of his what's left of his stock ponds right now, right? And that could happen as we move into the winter. So really, in the short term, we might get a significant cold blast. Obviously, that's important for cropping systems as well. But as we go out into the seasonal outlook, maybe December, January, February, the next 3 months, it starts to look like that La Nina pattern, and it should, because that's probably going to be the most important feature in what happens over this window of time. We might get individual rainfall events and so on, but overall it looks like drier than normal and kind of about normal in terms of its temperatures, except maybe further in the southeast and in the southwest. That's kind of the outlook. As we go even further, the outlook is right here in the middle. We're right on the middle, right? We don't really know. This is where our predictive skill is not great. As further out we go, driven in part by a weakening La Nina, so that also adds complexity, but probably still dry, and certainly the signal is probably going to be above normal in terms of temperature. So overall we'll probably have a warm spring, but we'll probably have a few of those cold air outbreaks in the middle and between now and then, and that's living in Oklahoma, I guess, right? From a tool standpoint, resources, always use your Mesonet if you're in this region, especially in Oklahoma. If you don't know what the Oklahoma Mesonet is, a fantastic tool. Wes is up here. I'm going to point to Wes and say he can answer all your questions about the Mesonet. Of course, embedded within the Mesonet website is the ag web. There's actually a nice button here, and all sorts of ag products that have been developed here on campus here over the years, working with the team, the Mesonet team, and folks at OU to try to provide resources for you. So that's good. That's a good resource. Some people ask me who's the meteorologist that I should watch on TV. No comment. All I can say is none of the chiefs are my former students. Some of them that do work at the stations are. And the best thing about that is I can tell them to stop being so darn dramatic. But what I would recommend is the folks at the National Weather Service. They provide local forecasts. They actually live in the communities that they're forecasting for. They try to do it a little bit more. Weather.gov, I trust these people. And most of them, by the way, are OU grads. Now that might be good, that might be bad, but there are a lot of OU grads working in the Weather Service to try to protect lives and property, both at the local level. And so there's great forecast tools embedded within the Weather Service. So I would always recommend weather.gov. You might have a TV meteorologist, by the way, that you love. That's great. I'm okay with that. But I'm not going to recommend any of them over the others at this point. There's also the Climate Prediction Center. This is where they produce some of those drought outlooks and some of those other outlooks that I showed. Those are important so that you can get to these resources online if you're interested at some of those areas. And then sort of looking, my summary in terms of this whole process is if we're looking out into the future, especially from an agricultural perspective, drought is here, probably not going anywhere in the short term. It's going to be a challenge, and because there's likely little change over the next 3 to 6 months. The long term, bye-bye La Nina. That would be great for this region. We need to recover. And then one of the most important aspects, though, is even if we get by La Nina, some of these local feedbacks might actually persist the drought through the summer of next year. I hope that I am wrong, and you can all tell me about it later, to be honest with you. I would sincerely hope that I am wrong, but I think we have to contend with the fact that it's probably going to be dry out into the next few months. Although the temperature standpoint, we could get some rain at intermittent times. Temperature standpoint is going to be warmer than normal generally with some of these cold shots. So that's kind of where we're headed for the next 3 to 6 months. And so from there, I'm done. Any questions? Yes, sir.
What's actually determining, what factors determine the temperature in the Pacific? In other words, what's going to change from La Nina to El Nino?
You want the real technical answer? I said, do you want the real technical answer, or so the well, I think everybody's jumped in the ocean at some point, right? It's a fluid, and so there are circulations in the ocean, just like there are circulations in the atmosphere. When we get these La Nina periods, we actually get really what they call strong upwelling. So we got horizontal circulations, but then we have water that comes up from the deep depths, and that's why it's cool, because we get upwelling. That cooler water actually makes its way to the surface. It's actually really important because from an ocean standpoint, it's great for the oceans, provides a lot of nutrients, and the oceans tend to thrive in those conditions. What ends up happening is it's in a more enhanced state. So what we actually need are features, and this is often driven, it seems like, by large-scale atmospheric processes and convection in the Western Pacific to produce what we call Kelvin waves that move from west to east across the equatorial Pacific to disrupt this strong upwelling circulation that we've got going. So what is really the important driver is actually, in order to create that environment, make that environment change, things that happen in the Western Pacific from a weather standpoint and climate standpoint, meaning lots more thunderstorms near the Philippines, lots more thunderstorms near Indonesia, to disrupt that portion of the circulation and send Kelvin waves back across the Pacific Ocean. That's the complicated. The uncomplicated is it's complicated. But we haven't had very strong tropical cyclone conditions in the Western Pacific in the last few years, and that's a function of this La Nina period. But that's what we need. Believe it or not, we need a lot of thunderstorms in the western part of the Pacific in order to start breaking this cycle.
How much temperature change by definition?
We are running about 3 degrees Fahrenheit below normal. That's it. But that's how big of just that much over that area changes the entire circulation of the atmosphere. And so even just getting it down to neutral will take a simple change of 3 degrees Fahrenheit, 1.5 degrees Celsius. Yes.
Is NOAA and OU connected?
Is what?
NOAA?
So NOAA is a federal agency, just like the USDA. We have a number of NOAA offices at OU. Is probably the best way of putting it. So if you ever get a chance, come down to the National Weather Center on the south end of campus. That's where Wes has his office, where my office is at as well. But also in those offices are not just the university offices, but some of our federal partners from NOAA are in that facility. But there are other NOAA offices in other locations too. That's the great thing about it. That was the whole vision of building the National Weather Center, is put all the meteorologists under one roof and we might talk to each other. And the answer to that is actually yes. We do. We talk a lot. It's great. And our students have the opportunity to learn from professionals, not just at the academic level, but in the field. And that's been one reason why we have so many of them now scattered across the National Weather Service, across the U.S. Good questions. Any others? Wes?
Point out those outlook maps that are so important to us in agriculture when they come out.
Those 8, 6 to 10 and the 8 to 14, and don't ask me why they overlap 8, 9, and 10 day. I don't know. I don't have a good answer for you, but those come out daily, so those will change as we have more confidence about how the weather is going to evolve over the next 2 weeks. Some of those maps, especially the seasonal maps, will be updated twice a month. Typically with an initial one towards the end of the month, so the next one will be coming out in about 10 days, and then on the last day of the month they'll finalize it for the upcoming month and the next 3 months. So. By the way, does anybody know what February of 2021's outlook was? If you go back to January, what was the January forecast for February of 2021 from a monthly forecast for temperature? Does anybody know for this region? It was above normal temperatures. And we ended up with our coldest February on record for the region. So again, I'm not saying we're bad, but we all know we're bad anyways, right? I get paid to be wrong all the time. So that's how it is. But Brian's kicking me off, but I'll be over here in the corner if you want to catch up to me, and I'll stay through lunch. So.
One quick question.
Okay.
Make it fast, Jake.
Long term, yes, certainly. Short term, it's more weather driven. So, and by the way, Jason and I work together too, time to time. So.
He does a great bit of work in Georgia. Has sent me one of my most recent PhD students or students going through my program, Michaela Smith, but longtime friend of Oklahoma State. Wes?
Thanks, Brian. Appreciate it and glad to be here today.
Oh, that was all.
Leave it off. It just sounds like this is working well. So what I just heard, Tyson and I were trying to decide how to break up this session. It doesn't matter because half y'all are leaving before Tyson talks anyway. So I can just talk, and Tyson, you get to go home whenever you want. You don't have to talk today. Right, so appreciate Brian inviting me, and the deal was Brian said, all right, we're going to invite you out there. What do you want to talk about? I sent him 4 or 5 topics, and I said, this is some of the stuff we're doing. We've been doing a lot of stuff with planter research. Y'all growing a lot of cotton out here now. We've been doing a lot of planter research on cotton, so we could talk about that. Randy can talk about that, though. He's not in administration anymore. He can cover that. I do a lot of irrigation work in Georgia. I don't know if y'all paid attention to those maps, but we're actually in a drought in Georgia a lot more than you might realize. We get a lot of rain, but if you saw the maps that were being shown, it's drought there. So we do a lot of irrigation to make sure our crops grow. We have sandy soils. Like, well, I don't know how relevant some of the work I do here would carry over. You know what? Let's make it fun and let's do what we don't normally do as an extension specialist and have a theoretical talk that we get to make up whatever we want to make up and just do whatever slides. So this is like my theoretical fun talk. So if you don't like it, too bad. This is like, there's no data here, there's nothing here, it's just fun. It's just for a discussion. So, I do welcome any interaction during it or after it that we're going to talk about. So let's go through it and see if you agree or disagree with my thought process on the future direction of on-farm autonomy. Turn this off. Oh, it's on. Is it there? Which way do I point it, Brian? Computer? There we go. Got to point it towards you. All right, good to know. So the first thing that we need to think about, we start using the term. When I hear the term, or most people that I talk to outside of ag hear the term autonomy, what do we think about initially? I think we think about robots. It's robotics. That's what we're talking about. We're going towards, we're moving towards that. And about 3 or 4 months ago, there's a Farm Press article that actually had this in it, and I thought that was good because we've been talking about it some. But it says, what is it? Or are we talking about ag robotics? Not necessarily. We need to actually divide that into 2 different categories. And our 2 different categories are going to be automated or autonomous there. And automated is just the control of some sort of agricultural operation. Whatever operation that may be, or some sort of function. That's removing the operator, the driver from the equipment is equating to robotic at that point, right? And so we do have a lot of robotic work that's coming out, that's being released, et cetera. We're going to talk about that later into here. But is it fully robotic or autonomous without humans, or where is this at? So that's what we need to think about. Don't automatically, when we talk about automation or on-farm automation, talk about non-human interference or non-human operations in robotics. So I want to refocus us as we move through this. So the next thing we got to do is, where do we currently stand and what are we currently doing? And I didn't even touch on this slide. I kind of have a where are we moving forward to, but what we need to think about is, what are we comfortable with moving forward to? So if we know where we're at, where are we ready to go? And if I sit here and poll John and said, all right, we've got the robot ready to go. Are we ready on the farm to just turn that thing loose and go? Are you comfortable getting out of the tractor and just sitting in the truck or sitting at home and letting it roll? I don't know if as a culture, we're quite ready for that in general, right? We're probably getting closer and closer, but we're ready to relinquish that control. So what we have to ask, is what percentage do we already have some sort of automation on? And I think it depends on what type of farm, what we're doing, what the operation is there. What is it? Who's interested in doing this? It's getting funny that as we start looking on the harvest side in Georgia, some questions that I'm getting more and more on the cotton harvest side, and I'm sure y'all get it here too, is looking at automating the ginning process more. We've got RFID capabilities around us. We've got more and more people that are no longer wanting to pay somebody to go out and scan bales or mark bales in the yard, right? They're wanting to automate that process. So that's the form of autonomy as it moves it through. So why are they interested in it? What do they tell me? Well, they're tired of paying somebody to be out there to do that. They realize they can invest a few $1,000s and replace that person in that particular operation and probably be more accurate and have more accurate records than what was happening before. All right, so what hinders it? And we'll talk about that a little bit as we move forward, but why do we not see more automation moving on the farm level, and where are we at? So I took this picture about 2 or 3 weeks ago on the way to a CCA training. So it's the first time I've seen one of these. Maybe y'all saw these. I actually passed something similar on the way in from Tulsa 2 days ago. Can y'all tell what this is? Maybe that picture doesn't do it justice. I shouldn't have took it driving down the road at 60 miles an hour, right? So let me explain the picture a little bit, but it was like perfect timing for this talk, I thought. If you can see it from the picture to your right, that you're looking at right there, that's a line of cars, right? They're doing highway work. We're on a 2-lane highway in the middle of the country in back road nowhere, Georgia. Guess what? Who's missing from that picture? And what has that replaced? That guy that sat on the 5-gallon bucket and just looked pissed off all day and rotated the flag, right? He's not there anymore. That's like I said, this is the first one I've seen. Have y'all seen any of these yet?
Yes.
Yeah, so they've got them. I thought that's it. We talked about anybody can do that job. Well, guess what? We got a robot doing that job now, and it's starting to move across. So I thought this thing was pretty cool. Nobody was around it on either side. We stopped on one side. It had the little arm down. It raised the arm. They were stopped on the other side. I don't know how it was controlled. I didn't take time to that day I was driving through to look at it, and I haven't looked into it, but I thought that was pretty cool. Even in the highway industry, obviously we're moving there. It's gone. That's one of our lower tier jobs that now we no longer have a need for. All right, so we mentioned this earlier, but how do we think about it and where we're at? We automatically think about robots. I just threw some pictures up there, and where is that? And we need to think about how we define on-farm automation when we look at this. So let's look at it. And I kind of broke it out into some categories here for you to look at where we can do. I already said this, automation and or robotics are not necessarily the same thing, right? Automation is one control feature. Robotics are autonomous at that. They can be autonomous at that point. They can fulfill several purposes, and we're going to hit some of these purposes as we move through this talk. A lot of times we're going to try to replace humans doing repetitive or dangerous tasks, right? That's what we looked at to start with. For example, on the highway right there, somebody standing there holding the flag all day being pissed off for a 5-gallon bucket to sit on, right? So he's good. We don't have to worry about that. That's a repetitive task that we can now have something that replaces that. Picture I've got in the bottom right corner, for example, is a small robot that just moves plants and pots around in a nursery, right? Instead of paying somebody to go out there that's bending over, picking up pots, moving them, that system gets a predefined schedule on where it needs to move what pots where, moves it around. Reduced labor requirements. So I didn't even hit this, but what's one of the biggest problems we've probably seen since COVID has ended or since we've gotten back close to normal? Nobody wants to work anymore, right? And that's everywhere. There's stores shut down, there's restaurants shut down, and it's gotten a little bit better, but everywhere is understaffed right now, right? So if we can't find labor and what we would call more unskilled labor to do some of these tasks on the daily basis, we've got to find some way to replace them. So this is some of our solutions as we're moving forward to that. There's got people that don't want to do these anymore, and now we're going to replace that with robots. In that case, a lot of times it makes operations more efficient. All of a sudden that we don't have to have breaks, we don't have to have time windows on operations, right? We're back to the limitations of what the robot can do and or maintenance time on that particular system. We can make management strategy changes at that point, just depending on how we operate. And then we can free up labor actually for other tasks, right? So now we can reallocate where we feel like we needed something else to move forward a little faster. So let's move back for a minute and let's talk about production ag, and let's step through it and say, where do we have opportunity and or, a potential for automation in agriculture? And so I went through the field operations, and I'm going to go through each one of these and talk about how we have an opportunity for automation and or already have that on the farm. And so when I do this talk, I didn't do it here, I should have asked. I like to ask at the beginning, how many of y'all have automation on your farm? And I talked to a group of farmers not long ago when I was kind of talking about this, and very few, 2 or 3 raised their hand. And then by the time I got done with the talk, they all raised their hand. I said, well, that's good. We need to recognize first that this is what we're doing, and then think about how we can implement and or utilize that technology to the full potential. So that's my extension portion of this talk. When you get done listening to the next 5, 10, 15 slides, step back and say, what do I have on my farm right now? What have I considered adopting on my farm that fits in those categories, and how can that improve my farm operation and or my production operation or my bottom end somehow? So let's move through these. So are there other opportunities that we can control better than others, ones that we can focus on better than others, or ones that we're already there on? So some of the typical ones that I had listed: tillage, spraying, planting, fertilizer application, irrigation management, and harvest. That's our big operations in any row crop operation, right? That's from beginning to end. That's where we're at and where they stand. So the first type of automation that we saw widely adopted across all of agriculture was what? It's up there. I gave you the answer. Auto steer, right? How many of y'all that farm have auto steer on your farm? Probably about everybody, right? Even Jennifer has it. I get to pick on Jennifer because we travel together. I don't think she's in the room now, so I can pick on her even more, right? No, she's over there. She's over there. See, they have it. Even in doing cattle farms, right? They're utilizing it to some sort, form, or fashion. So, spraying. Spraying has a lot of opportunity when we look at it from automation. So we can talk about overlap control first off. That was one of our more basic ones. Rate control, right? You can put rate controllers on sprayers for a few $1,000. That's automation. You're not thinking about it anymore. Then your calibration's independent of speed. You can apply pulse width modulation. So we've got individual nozzle control. Because of that, we've got better flow rate control, better application control. And then guess what? The See and Spray technologies are automatic control systems. So we see a lot of that now. We're talking push from John Deere, See and Spray. We can do this now. We can identify when we need to and target what we want to do. And so there's a lot more that's going into See and Spray than some of the other technologies, right? But at the same time, it is just an automated. It's not a robot. You're still out there operating the system. So just threw a quick picture up there. That was 2 years ago, I think, when they announced the launch of See and Spray on their 400 and 600 series sprayers. All right, planter technology. So I've done a lot of research with planters over the past few years. I'm going to talk through a bunch of things on here and a lot of the control systems we have. So it's one of the most important operations we have, right? If we fail at the beginning of a stand establishment, we're either replanting or we've set ourselves behind. And depending on how bad that failure is, that's a big investment in seed again, and then we're also behind on production, and that's usually a yield loss associated with that. So if we can better target where we're at based on those environmental conditions while we put the seed in the ground, then we know where to best place it to maximize emergence. So that's a lot of work that we've been working on the back end to feed into these systems to know where they need to be. The 3 parts that I picked on the planter system that we're going to look at and talk about that are automated right now, that you can buy a control system for those, and probably already have some sort of control system on your planter for those. The metering system, right? The downforce control system, and then the depth control. So let's look at it. Metering system, we still see some, but we've kind of moved, I think, more away from hydraulic. We've got a few guys that have that in Georgia, but more of our guys, if they're moving forward, they're all going to the electronic controlled meters, right? So both John Deere and Precision Planting, Case, any of your big planter, Kinsey, any of your big planter manufacturers now offer some sort of electronic control on your seed meter. And the opportunities there are really, really nice. A lot of that is seed rate control or potentially matching up meter speed with ground speed. So, and then we also have advanced seed delivery. We've done a lot of research on cotton and corn in Georgia with some of the advanced seed delivery, whether it's the brush belt or speed tube there. Excuse my chopped picture, but I thought that was a cool picture of the speed tube. I had to take it in 2 pictures to get it there, but it was a clear picture of it so you could really see what's going on in there. So we've got that system. Then we move on to downforce control. I would assume it's probably just as critical and important here as what it is in Georgia. Tyson and I were talking yesterday about variability in western Tennessee. Same thing. What we see a lot in Georgia, we go from a really light sandy soil to a heavier clay soil. Now, our heavy clay soils are not Oklahoma clay. I can say that in Georgia, but we do have some red soils down there. And one of our challenges we see a lot of times, we've got guys that either are not using downforce at all because some of our lighter soils we were having issues with. And when we have that case, if you go through their field and you see some of those red hills in that field, they have little to no crop emergence usually, especially on crops like cotton, because we're not getting the seed where we need to be. And then peanuts are another crop that's really sensitive to that seed depth. So we've done a lot of work talking about where downforce settings need to be to match soil texture, soil type, and soil moisture in our state in all 3 of those crops, so that our producers can feel more confident that this is where we need to be. And so where it also comes back to, we've got a lot of our producers who pulled all their downforce systems off to actually at least go back and put springs or some sort of pneumatic system back on their planter so that they know that we're actually achieving an appropriate seed depth. But then we've had a lot of producers that have moved forward from spring force systems to either a pneumatic or a hydraulic system, right? Most of your new planters you will buy now will come standard with pneumatic on it, but we also have a hydraulic option to incorporate. Seed depth placement, again, it's a threefold thing or twofold thing. We need a combination of downforce and depth, and then we've got to look at our environmental conditions. We've shown a lot of work, especially on smaller seeds, and I'm going to leave smaller seeds broad, but if we're not careful, soil's too dry, soil's too hot, soil's too wet, something's going on, and we don't put that seed where it needs to be for that particular condition, we're not going to get that seed up and going. A lot of our work has been on cotton just because it's our #1 crop. When we look at other crops, we notice the same thing with all of those. So in this case, I'm showing Precision Planting Smart Depth. Has any of y'all worked with that or used that system? Not yet? We're working with it a little bit in Georgia. We've got on some of our test fields that we're looking at utilizing it. How about that Smart Firmer that you see right there? Do you know what that is or what it does? Let's see a few heads shaking yes. So Smart Firmer is measuring about 5 or 6 different things during planting, and then it's giving you kind of a combination of what your furrow looks like. It's giving you soil moisture and an estimation of soil electroconductivity, soil temperature. It's also measuring the trash content in that furrow at the time and compiling some of that data. So it's nice to have that information to know, are we having drastic changes in soil moisture as we plant across the field? What do you think my farmers have told me they use it for? We have some that have it, and I said, well, how do you use this? I know how I would use it. I would adjust my seed depth based on moisture. That's where I'm at, because that's what I've seen, that if I can chase that moisture a little bit where I'm at, or that temperature in some cases, I can maximize emergence. What do you think they've told me? If you're a farmer and you're using it, what would you use it for? Nobody? They just told me that they use it to know when to stop planting. Once they get below a moisture threshold, they just quit until they can get rain or get irrigation on that field. Well, that's a valid point, right? They said, all right, at least it gives them that opportunity. So if we look at just planters in general, now we have a full suite of technologies that we're no longer having to make decisions sitting in the cab based on what we think we're seeing in the field, but we're setting the systems up based on what we know that we got in the field, and then they're automatically controlling that for us. So that's where we stand. All right, y'all are the state expert across the nation in this. I almost removed these slides, right? You've been beat on this by probably Brian, by everybody before Brian, by Randy, by everybody else, but sensor-based nutrient management, fertilizer application, wherever it's at, right? That's a hot topic. It's been up and down, in and out, maybe not adopted the way we would like to see it adopted across, but this is a really cool technology. I would say that when we look at going out to the field and making decisions, if we have a way, whether that's a satellite imagery, whether that's a real-time sensor like I've got in those 2 pictures there, whether that's something else going on, that we have a feedback control loop that we're making real-time adjustments on the go based on predetermined algorithm. That's automation there. Irrigation management. Irrigation is kind of cool. It's one of probably the forefront runners in on-farm automation right now. Our biggest hindrance, and this goes with everything, and I didn't even get in the legal side in any of this talk because that's not the fun stuff to talk about. But right now, if you've got remote pivot monitoring and control, you can start your pivot from anywhere. If I'm standing here and I got it, I could start my pivot up in Georgia, standing right here today, right? And so I can get some sort of monitoring in the field, whether that's soil moisture sensors, whether that's an app or an online tool that tells me when that crop needs irrigated. I know, all right, I need to irrigate this crop now, and I can run that system without having to physically be there at the time. And irrigation companies have worked really hard, like a lot of our other big ag companies, to create these connected farms where they'll have weather stations, soil moisture sensor networks, and pivots all linked into one app so we can see everything that's going on across that farm and make decisions real time. Harvest is really cool. First off, I don't know if you can see in that picture. I had to throw it up there. I can't see from here, so y'all can't see. You probably can't tell. You know, and Kinsey was one of the first ones to release it, but now about everyone's got this autonomous grain cart, right? There's nobody sitting in that cab at that time, right? So we're doing two-way communications that at this point, when we start filling up our combine and we know we're getting close to unloading, we don't have to have somebody sitting in that tractor cab. We push a call button and that tractor brings itself over automatically, communicates with that combine, follows it, and then we unload on the go. And so there's a lot of implications to that right there. No longer is the driver having to try to match speeds and do everything else. That's going to do it all for us. The other things that I thought was cool, if you look, Case and John Deere both have won awards over the past year or two for on-the-go adjustment in their combines. And so what they're doing is they have a series of sensors that are implemented throughout that system that is measuring the grain movement through and looking at losses and looking at biomass movement through it and making real-time adjustments on the go to maximize the yield that's being brought in that system and minimize losses. So, you know, we're moving towards where you no longer have to be the expert in the field and keep checking all that. This system's going to do it for you while you harvest and while you're on the go. All right. So we've talked about this. Let's move forward into the discussion and kind of talk about, you know, where we're at in the integration of robotics into it. I hit some of these: repetitive operations, dangerous operations, efficiency improvements, replace humans, time-consuming tasks, and then agronomic management changes. Quick time check. All right, we're doing good. I'm gonna leave you plenty of time, Tyson, to talk to nobody. Stretch it on that. No, I'm gonna slow. I'm gonna go really fast now, just so you got to get up here. Kidding. So, talk about crop harvest. And so when we start looking at crop harvest and talk about, we got specialty crop harvesters out in the field, and that's something especially you get south in Florida and then some of us in South Georgia, we have a lot of specialty crops that we deal with there, and we have looking at how do we harvest and handle those systems for the field. How do we optimize fruit quality? How do we minimize damage? How do we sort those fruits during that time, et cetera? We look at spraying, planting and transplanting. I just threw that picture up there, that autonomous John Deere tractor with the planter behind it. I just thought it was a unique picture when we were looking at it. So now we can plant basically all the time as long as the environmental conditions are correct, right? I just told you your planter control system. So if you understand on your farm where my planter needs to be for a particular condition, let this robot go and it can just do all the planting for you, right? You don't have to worry about if it's day, night, or where it's at. You just have to worry about more extreme weather conditions, whether it's too much rain or too little. In that case, I kind of mentioned this: the sorting, grading, sizing, you know, looking at machine vision systems, quality sorting, et cetera. So dangerous operations, we are seeing more and more. This year at Sunbelt Ag Expo, our farm show in the Southeast, released a new autonomous sprayer. So when you look at orchard productions or you look at certain operations especially, we have guys that are usually operating open cab tractors with air blast sprayers, right? And so we're blowing a lot of chemical out there. And so this is a perfect opportunity that we can replace that tractor operator with just a robot to go out there and do that spraying for us. Putting people out in just the environment in general, you know, whether the conditions are too cold, too hot, et cetera, out there. If we can get a robot to handle that, then they're no longer out there. Reduce proximity to dangerous equipment, right? If we have something that we're prone to someone getting hurt or something happening there, if we can replace that person with a robot. And then reduce strain and fatigue. Efficiency, more precise applications. So if we're looking at a system that we can monitor the canopy at any given time and understand size of biomass, we know what rates that we may need to apply, and we know where we need to target those rates at that given time. We mentioned precision irrigation. I do a lot of research in that, and it is phenomenal the gains that we can get back by precisely irrigating in a lot of our crops, and I'm sure y'all would see the same thing here. Precision planting, weeding, and then hopefully lower downtime when we look at that. I mentioned replace humans in time-consuming tasks. We talked about spraying, talked about a big topic. It's probably a big topic here too. UAV spraying or drone spraying, a big topic here right now. It's a huge topic in Georgia, not yet. Y'all said maybe not. It's a really, really big hot topic right now in Georgia. Sorting or weeding. We had what precipitated some of me and some of my fellow colleagues to start talking about this and looking at this a little bit deeper is we have a large vegetable farm in Tift County where our campus is at, where I'm located. And he may be the largest vegetable farmer in our state. What he also does besides vegetables is he grows pine seedlings. And so I don't know, I don't think y'all do a lot of reseeded on pines out here. We do a ton of that in our area, but he grows pine seedlings that get shipped all across the U.S. And one of the processes that he takes the seeds, and he has a special machine, I think that was made in Switzerland. I've watched the process, puts the mini seeds in little bitty cups, and then basically put those out for germination. Well, he reuses these trays, and they have to be washed with a particular chemical to prevent any disease overlap from seedling growth to seedling growth when he ships those out. And he pays people to stand out there and wash these. He made us come out there today and watch the process of, you see this stuff that these guys have to do, and he said there's got to be a way y'all can invent a robot at UGA to eliminate this. He wanted it gone. He just wanted something to sit there and wash the tray and move it over, wash the tray, move it over, wash the tray and move it over, just because he felt like a robot would be more efficient and effective at doing that. So agronomic management changes, I think this one's unique. It can be a controversial topic, it says potential shift to organic, but if we're talking about we can mechanically handle stuff now, maybe we can reduce some of our chemical application or our chemical needs in the fields then. Mechanical weeding, precision management of inputs, when we look at that, different planting patterns, right? So we've talked about that a lot. How do we maximize our agronomic operations? Is the 36 or 30 or 38 or 40-inch row actually maximizing when we're looking at that, or is there some other plant spacing? If you talk to agronomists, I've always been told the diamond pattern on corn is optimization, right? So if we can perfectly align on a twin row corn pattern, that kind of diamond where the seeds are offset, that's where we need to be to maximize light interception. No, we can potentially do this better here. There's different crops we could grow because we're able to manage it that way then. All right, so that's kind of the end of my theoretical talk. I'll stop for 2 seconds. Are there anything you want to discuss there? What I want to share with you, I reached out to 2 colleagues of mine that I work nationally with, got their contact right there, and I asked them to send just a few slides because I think it's always interesting to see what universities are doing across the nation in this realm. So this kind of may never make it to the market, but you know what we're researching and working on. I have time for that, Brian? I say check time. We're good. All right, no questions? Yes.
That's the biggest thing that I see with all, whether it be, autonomous spraying or anything like that, is you have to have somebody there on the ground reloading it at that site.
Yep.
How many acres can they actually cover, given the right conditions to actually spray?
So you brought up a really good point. You got to table that point for about 3 or 4 more slides. Yes, I was about to do that. So he said one of the biggest problems with a lot of the autonomous and robotic work is one, the cost of them and the scale of those and being able to implement those with completely autonomously. Because he's saying we still need someone there in the field. Right, if we're doing spraying, somebody's got to be there to reload those. If we're doing planting, somebody's got to be there to check that. And making those affordable enough that we can still reach the same field capacity that we can with a 12-row or 24-row planter or something along the lines of that, right? So where that scalability and the affordability is at, that's one of our biggest problems right now, and that's exactly right. Any other discussion on this?
And I apologize if you answered this in your talk and I zoned it out. I'm thinking about the process of development. Like on the farm, we all always have ideas, like your guy who mentioned.
Right.
Do you work with manufacturers? Like once an idea comes to you, do you work with a manufacturer, or is it just like, okay, we figured out how this can be done, now somebody else has to continue to do it? How does that process work?
Can we table your question too? The reason I say that is the nice thing is what I'm about to cover. It's a perfect question too. How do we work as a university to work through that process? Maybe I need to step forward. Y'all's the questions I've answered. Let's step forward. So All right, I'm going to go back to your question for a minute, and I have it in here twice. So robotic cotton harvest, that's something we've been working on at UGA for about 5 or 6 years now, and the iterations of those have changed dramatically in the time I've been there. We've had about 4 or 5 different grad students that have worked on this, and the very beginning, what they started on is we just had to figure out how to identify a cotton ball first. Then we had to identify how to get something to the cotton ball, right? And now we've got to learn and work on refining, and that's what some of these pictures are. Now that we've found the cotton ball, we can move something to it. What's our best end effector to actually remove that cotton ball from the plant, right? And so that's where we're at right now. Back to your unit. So we got a graph there. We work on this. Here's our 6-row cotton picker, our acres per hour, number of harvested units that are there. So we've left that as 1, obviously. Acres per hour, that system can get up to 7 acres per hour easily. So how do we replace that, and how fast do these other units need to work? So that graph gives you a little bit of an idea right there, how fast this system can travel through the field and how many of those we will need to replace that. So 1/4 mile an hour, if we're covering 1 acre per hour, that means we need 20 units. So that's how that graph works. And so that tells you size, scale, affordability, how fast we actually need to be picking this cotton at. If we can move that up to 2 miles an hour, get our capacity up around 6 acres per hour in this particular system, we need about 10 units, right? So it's kind of amazing to look at that, the number of units that are there. This project, to answer your question, this particular project is a joint venture between Cotton Incorporated, Case New Holland, and University of Georgia. So we're all 3 working on it. There's funding come from the other 2 external sources with us. And usually what's going to happen is we will develop, to go a little deeper from our side, we would develop something that is usable, but then it would go to mass production to them. It would be licensed to them to actually make the end. So like the picture I'm showing, and this will show up on the screen. This is our new end effector design right here, if you see this. And you notice what it looks like. It looks a lot like a cotton picker that you see now, right? It's just mini spindles sitting on that system, and it actually has a vacuum line back behind it, and they had to put these little arms on it to guide the plant in a little bit better. So now we've just miniaturized the curtain cotton head, and we would just license that potentially to John Deere or C&H. They would probably make some improvements on it and have it at a mass production scale. That's the way we've been working with them right now on this particular project. All right?
So when you're up that 10 or 12 units to get the 6 acres per hour, does that include moving the material away from the machine, or is that just down the road?
Right now, this is just down the road. That's our next problem is, okay, so right now, we're able to load up 5,000 pounds on one cotton harvester, right? So how do we get this material back? That's next step. We're just looking at harvest right now, unfortunately, right? We're not even looking at material handling yet. So I did, and I would be interested to see where he took it. My grad student who just started his PhD, they had a class project in systems processing, and I told him that was the problem they needed to address. The project was due yesterday or the day before, and I told him I wanted a copy of it after they got done. So I'd be interested to see on the material handling side how they address that and how they decide to move it. But we are starting to think about that now that we can feasibly, let's say with quotes, feasibly robotically harvest cotton. All right, stage defoliation. So this one's really cool. And really quick data if you want to look at it, if you know anything about cotton. All I'm going to say, so we don't go into it too early, if you look at our early treatment on any of these or versus the late treatment throughout, so the E and the L, early and late, early is always better fiber quality, right? So we know that if cotton opens from the bottom of the plant to the top of the plant, cotton that sits out there longer is going to degrade fiber quality. So what we've been doing, and we've set up actually that, it's not, and you'll see this in a few minutes, this robot gets used for about 12 different things. And you'll notice that that's what we're trying to target is it's not going to do one thing. We put implements on it. So one thing this robot does is we have some specialized spray hoods on it that we go out to this field, and it might be a little hard to see. You might just say, well, Tyson says y'all just got a lot of regrowth. You just didn't do a good job defoliating. But if you really look at this, what we did is we sprayed only the bottom half of this plant at this time, and we left the top half of that plant alive, and then we went out and harvested only the bottom half of that plant and said, what are the fiber quality implications of that? Is it worth it to do stage defoliation? Is it worth it to go out and do selective harvest, in this case on cotton? So to start with, our numbers are better. Economically, I'm not sure yet, but fiber quality numbers look better, and we're maintaining yield by doing that. This one's cool, laser weeding. One of my colleagues is working on this one. Have any of y'all seen any of this? I've seen some of it, a little bit. Brian's seen some of it. So this is a way, if we need to, if we have chemical resistant weeds, we got to mechanically get rid of them somehow. His 2 options he was working at, he had a saw blade and he had a laser. Saw blade's a little dangerous, obviously. You had to be careful with the grad students working around those on the robot. I might need your help on these videos. I wish you could you click the videos for me? So here's his laser. You can see the weed up top. Yep, there you go. So he's done a lot of work in, this is Glenn Raines, I put his contact up there before. They've done a lot of work in determining laser power and then what actually kills that weed. So depending on where we cut that weed off or burn that weed off, it's going to die or it's going to come back, and then the stage of it. So he's put all that research in that we looked at that a weed scientist would, so we know when we need to go out there and actually kill them and at what voltage to actually permanently terminate that weed. 2 minutes. Remote pest monitoring, this is a really cool system that we've got, and so why this one is cool, and it's probably something to be really applicable in a state like Oklahoma. One of our problems in the summer, because we have such large vegetable production, is whiteflies. And whiteflies cause sticky cotton. I'm not supposed to say that, I'm not supposed to put that out there, but that's really a big issue at the spinning mill. If we get high whitefly populations in Georgia, and it's hard to get rid of them. And so how we know that we start getting them is we've set up basically an Internet of Things wireless communication system where we have visual imaging happening all the time. That yellow paper that you see in there is just sticky paper. As whiteflies get on it, we can do a quick estimation of what our population is in a particular area of the state. We have these located throughout the state now, and we know, all right, we're starting to get a high whitefly population here. Guys, be prepared. That means that it's going to start exploding somewhere else, or we need to stay on top of our spray. And so if you can think of any pest, could apply it to disease issues, potential, or anything like that, so we can stay ahead of that. So I thought this one was kind of cool that we're moving forward in an actual application we're using right now.
Wes, is that DTN or DNN? What's DNN?
What was DNN? It is DNN, and I cannot remember right now.
That's fine.
I knew then, but now I'm out of that mind state. Sorry. All right, so let's go to University of Nebraska-Lincoln. This is Santosh Pitla that shared these slides with me. And so same thing, so we look at our scalability. And so back to answer your question, that's what we're trying to address that at the university level. This is just an example slide he has. If we're replacing that 600 horsepower tractor, what do we need? 10 ag robots at 60 horsepower. If we're doing 200 acres, can we get by with 3? If we're doing 400 acres, can we get by with 6? If we're doing larger than that, do we need the 9 there? Do we need 10? Where does it need to be? And then we start looking at and talking about swarm operations and inter-robot communications. I think I left that slide in here. If you notice, a lot of our work across universities, that's why I like to share this, ends up coming back to similar style robots right now that are multifunction. And I've got some of his pictures in here on some of the things that he's doing. You can click that second video too, and it'll just run. So these are their inter-row robots. They call it the RASP inter-row. And so they're just going in the rows and doing, whether that's phenotyping, whether that's monitoring for weeds, whether that's monitoring for plant growth and health, or whatever's going on at that time. You notice the one that was in the corn, the green cornfield, to me it looked like it had a humidistat or something on the top. It had some sort of weather sensor on top of that one. And then the other one, they're just showing that, hey, this is what this robot's doing. It's able to operate within the row and then do some sort of function in season. Not necessarily a large function, but a small robot that gives us information about that field. All right, so here's their flex row or flexible structured robot, very similar to the one that we have at UGA, hydraulically driven, smaller motor on the thing, but it can do a lot of different things. And so this one, he's got, I've showed you 4 different things that Santosh is doing with it. They're doing phenotyping in the top left, so they're collecting stuff like plant height, current plant health, a multitude of other factors about those crops at that time. Field object identification, working to make sure we can identify objects that are not crops, that do not belong in that field, or objects that we should avoid at any given time in the field. And then that bottom right picture, to me, was really cool. They started working on replanting. We've been doing that at University of Georgia too. I didn't even put the slides in here. That red robot we have a single row unit that we go out and scout during the season. And if we have skips in the field that are larger than a certain size, we send the robot back out and it'll lower the row unit based on GPS coordinates back in those sizes and do replanting. So now you could send one of these mini systems out where you didn't have to replant the whole field, but you could just replant the skips in the field that are issues. And that's some of the work Santosh has been doing with this flex row. He's got 2 row units that are mounted under this system that can raise and lower at any given time. All right, so really quick on those. I just wanted you to see what, like I said, a couple of colleagues were doing that. Even though you're seeing a lot of stuff released by industry, we're not being left behind in academics. I think we're pushing stuff a lot. We're doing a lot of neat and interesting things. But from the farm perspective, don't sell yourself short. let's not get caught up in looking at just robotics and looking at where we may be 10, 15, 20 years. I don't know when we'll replace that. I don't think it's 5 years. I don't think it's 10 years. We may slowly see some small things like that IRAS come in where we can do some more scouting. But I would say think about what you have available to you now and what can make your operation better on a day-to-day basis. I tried to talk through some of those technologies that are currently commercially available that we've done a lot of research on, that a lot of other universities have, that we can utilize today to make production decisions or make production easier and better for us. So moving forward, I don't know, I'm seeing more remote sensing coming back to life. A lot of satellite imagery is being used again. Mentioned drone spraying, hot topic right now in our state. I stay as far away from it as I can. I don't want anything to do with it yet. I got a colleague that luckily he likes to deal with it, so I'm letting him handle that. We have high levels of automation. We don't have high levels of robotics quite yet in ag, but they're coming and they're on the future. So with that, there's my contact. It won't be around much longer. We got a flight in Tulsa to catch here soon, but I've enjoyed the time here and appreciate Brian inviting me out. Hopefully y'all got something good out of the talk, at least thought a little bit about, what's there and feel a little more educated on where we're at now. Or you can call it all BS, right? That's what I said. It's the fun thing about these talks with no data.
Thanks, Wes. Questions? Any questions for Wes? Dr. Porter, yes, a couple.
Here. Do it.
All right, I don't know. So I haven't worked with them, but I've done a lot of working around them. So the concept of the drones is really you're going to need the swarm as beneficial, but the autonomous swarms are not coming in to take over 1,000 acres of spray. Their application is wet ground, small areas up in Ohio where maybe it was too wet to get a fungicide on a wheat crop and you had 1,000 acres to cover at a critical period. It's not going to be spraying over 20,000 acres in a week. So it's more site specific where you just can't get in big equipment when you need it or big equipment's not available.
So we in Georgia, because we're very humid in the summer and we have a lot of disease issues that'll flare up. And in combination, when disease issues come, you've been getting rainfall, right? You got high humidity, and that's perfect condition for disease. Brian said we can't always get either in all the vegetables are a big one for us. That's where we first started doing the drone spray, and we could spot spray some of those. When we saw a hot spot with remote sensing or scouting, hey, I've got a disease that's starting to outbreak in this field, send something either directly to it or there's parts of the field we could not spray. What has shocked me this year and some of last year's, we have had guys trying to defoliate cotton on large scales with those and saying they're just as efficient and effective as what our ground-based sprayers are. And my colleague's working on some of that data. He's presenting some of that research at Beltwide. Any of y'all do cotton right over New Orleans or look up his stuff. He had a grad student working on the spray patterns and droplet sizes and all of those, and can we actually do that? So, good question, though.
You had one? Chase, did you have one? Okay. No, yeah, so one of the things that on that pattern is trying to figure out how much invection, how much that downforce does to have a better coverage. And the VR, so we did, what was that conference in the summer? AgTech. We did basically a VR IPM or precision ag IPM, and it was all about identifying ahead of time and spot spraying insects, weeds, and disease and reducing your overall volume and trying to do that way. But if you got to spray a whole field, I would not do it with a swarm, especially if you go western Oklahoma and you got a mile-long run. Yeah, 40 acres an hour is what I'm hearing, but it's swarm, and it's a pit crew. You ought to video it and see these pit crews. What's a Rantizo? Probably is one of the better known. Yeah. All right, we got to move west. West is still going to be around. So our final speaker for this session is Dr. Tyson Raper. I've known Tyson since he was in grad school again, with kind of like with Wes, and so it's really exciting to have him come in here. He's worried that nobody in here grows cotton, but I assure him that a lot of our CCAs still have our cotton stretched from low to south. So I'm looking in this room right now, and our numbers are low, but about every one of them deals with cotton.
Excellent.
So you're in good shape.
Excellent. Well, thank you for the opportunity to speak today. My name is Tyson Raper. I'm the cotton specialist at the University of Tennessee. I want to start today. I'm going to talk about a national study and some of the results we've had from that study here in recent years. But to start, I got to point it that way. All right, over here. Is there a magic spot to? I got to point it at this. Okay. Oh, there we go. All right, but to start with, and I'm going to have some take-homes at the end that I kind of deliver to my growers. To start with, I want to tell you where I am and what I'm looking at when I look at a cotton acre. There's a lot of similarities between what I've got in Tennessee and what I think you have here in Oklahoma. When you think about cotton in the Mid-South, you probably think furrow irrigated. That is not the case. In Tennessee, we are 95% dry land. We've got lush, silt loam soils that we grow most of our cotton on. I'm located actually about right here. Red would be cotton. And this really dark green area, that would be the Mississippi Delta. The acres in Tennessee, the cotton acres in Tennessee, we have a very, very small fraction that will actually be in that really deep silt loam that in Arkansas would be hipped up and furrow irrigated. So my biggest limiting factors in Tennessee cotton production, number one is going to be heat units. I'm right there on the northern edge of the cotton belt. And number two, for most of my acres, it's going to be rainfall. So, and we're getting a lot of rainfall, relatively speaking, but still, I don't necessarily get it at the time I want it. So those are two major factors that are limiting yields, pretty similar, I think, to what you would have here in Oklahoma. A little bit about my program. We are an applied research and extension program. We do a lot of on-farm research scattered throughout all the cotton-producing regions in Tennessee, each of the large cotton-producing counties. We run a microgen, and a fairly large microgen, run about 5,000 samples a year through that microgen. And we use both these trials and that gen to generate variety trial results. So management and variety selection is extremely important to me. I spend a lot of my time focused on those two aspects of agronomics. And then we extend these results to our, obviously, agents and clientele. So, but a big portion of what we're doing, again, management, maturity, variety selection. So my main objective today is going to be to talk a little bit about some of the work we've done to update the heat unit system, the DD60 system that really the cotton specialists initially adopted in the early 80s. Why am I talking about that here today? And why did we do the research? Really, it was to help you maximize return on investment of each input. The heat unit system, the DD60 system for us in Tennessee, if we have a full understanding of how many heat units we're accumulating, how many we potentially may have left in the season, what we need to get to each of those growth stages, we can better select our cultivars, we can better terminate insecticides after our last effective bloom date. That's a big deal for us. And then finally, timing of those harvest aids. Well, actually, all three of these things, in my opinion, have changed quite a bit in the past 10, 15 years. And as we look forward to the technologies coming out, we're going to continue to see those change in the immediate future. All right, so I want to start with a very basic introduction of thermal time. And this is what when we talk about a heat unit, we're basically talking about thermal time. This is going to be the quantification of time spent above a base temperature. And for those in corn and soy, a lot of times we talk about DD50s. In small grains, we may talk about DD45s. This concept of thermal time, anybody have a guess when this originated? A year? Somebody throw out a number. What was that? 1945 is a good guess. That was really when we started to see corn and soy get refined. Any other guesses? Earlier, considerably earlier. We've been talking about plant thermal relations for several hundred years. 1735 was really the first time that somebody looked at temperature over a threshold and then correlated that back to plant growth. So we've spent a long time, and the calculations not changed much at all over that time frame. History in cotton, I mentioned the extension cotton specialists met in the early 80s and kind of settled with the base 60. Up to that point, we had discussions on whether it should be 50, 55, should it be 58, 59. About 1983, we settled on a base of 60. There are some exceptions, and Arizona is going to be one of those. They use a base of 55 with a max cap at 86. Most of the belt does not use that max cap. Most are going to, if you hear somebody talking heat units in cotton, most of the time it's going to be a base of 60 without a cap. And there have been some efforts to reevaluate, but very similar to the reason and how we settled on a base of 60, there's very little data. So we would be looking at maybe an observation out of one program or a number of observations over several years out of that one program. And then the scientists would get together and discuss, but we've not had a really structured look at heat units since 1983 when they really settled on that number. And I've got some references. SUPAC is one of them, and Silvertooth. Both of these, SUPAC wrote up the meeting there in 1983 for the Beltwide conferences about the discussion. And it's really interesting. A lot of the comments that he made in 1983 were the exact same comments that we discussed when we decided to come up with this study just a few years ago. Silvertooth is one of the scientists out of Arizona that really pushed the 55-86, and in an arid environment, that made a little bit more sense for them. That was out of pink bollworm modeling is the reason they settled on those temperatures. So this is a pretty simple concept. From a heat unit standpoint, you would think as we increase temperature, you should see an increase in the rate of growth and development. And that's really what this whole DD60 system is based on. There's a variety of different ways to consider how to accumulate these. The most simple way and the most widely used, we basically take the mean temperature and we're going to subtract that from our base temperature. We're going to accumulate that over the growing season, and that should give us an indication of where we are and where we should be from a growth and development standpoint. So I mentioned that SUPAC highlighted a lot of things that are still relevant to us today. A lot of the issues he stated very clearly in '83. Plant growth and development in this approach is assumed to be driven by temperature alone. And we absolutely know that is not the case. We saw earlier today Liebig's barrel and all the different staves. Any of those factors that are not sufficient or obviously could be the main reason that growth and development is limited. Water stress, nutrient deficiency, solar radiation, wide range there. Additionally, the relationship between plant growth and temperature is considered in almost all of these relationships as linear, and it is not linear. We know that, it's curvilinear. But in our calculations, we assume that it's, it excels up to a point, and without a cap, it continues to excel, right? So major limitation of this approach. We also assume that the lower threshold temperature is constant throughout the season. And then as an agronomist, I want heat early. I don't care so much about a cool night later in the year. We know that this cold stress early is not the same as cold stress late. There's a difference there. And finally, upper threshold is typically not included, as I mentioned. With the exception of Arizona, most of the belt's going to not use an upper cap. So cotton specialist in 17 visited and felt like there's an opportunity, there's reason here to reevaluate the heat unit system. First of all, we looked at average yield. So if you think about in 1983 where yields were, this is for Tennessee now. In 1983, yields were right there around 600 pounds. But this year, even with some marginal rainfall patterns, we're going to exceed 1,000 pounds, right? So fruiting patterns have changed. The plant appears to have changed a little bit. Part of that's through brooding. We felt like this might have caused the guidelines, this is how many heat units it takes to get to squaring, to flowering. We thought that they might have changed based on some of these yield improvements. We wanted to look at if the 60 base was still appropriate. We felt like we were seeing some maturity differences throughout the year, that 58 might be more appropriate than 60. We wanted to look at the possibility of including an upper threshold, and we wanted to see if these should vary throughout the year, right? The last one, and the one that I was most excited about, I can't tell you how many consultants I visit with, and they say, I had a massive fruit shed. I've had a week of cloudy weather. Let's say they get a big rainfall after that. They'll see all the fruit wash out the bottom of the field. This solar radiation, we felt like if we incorporated some measure of is it sunny or is it cloudy, that we could do a better job of predicting fruit retention, and therefore do a better job of predicting when we're going to get to that first square, first flower, cut out 60% of it. And, in all of this, think about what in 1983, the computing power that was available versus what we can get right now. these parameters, if we want site-specific rainfall, we can get that. Site-specific cloud cover, we can get that extrapolated, radar detected, have a pretty good feel. We could incorporate a lot more parameters into the model fairly easy compared to where we were in 1983. So this was a massive effort, and right there at the core was Cotton Incorporated and Auburn University. Really appreciate both of the support that Cotton Incorporated provide and some of the expertise that we had from a climatologist there at Auburn. We're now also working with a climatologist from NC State. So this was a massive undertaking across the entire cotton belt. It was a very simple trial. We spent a tremendous amount of time in the trial, but it was a very simple trial. And what we basically did at each location, we planted 3 varieties. We had an early maturing variety of Delta Pine 1612. We had a mid-maturing variety, Delta Pine 1646, and we had a late maturing variety, Delta Pine 1851. So we've got early, mid, late, all locations. These are replicated trials. We've got 4 reps in each location. Not a very big trial, but spent a tremendous amount of time in them. We had in all, I think the final analysis included about 28 locations. So in 2018 and 2019, all of the cotton specialists throughout the belt maintained at least one, and some of these locations consisted of, some of these cotton specialists maintained 2 locations. So tremendous amount of very, very large swath of locations. Again, this is likely the largest set of data we have, it clearly is, on evaluating whether 60 is appropriate or not. I mentioned we spent a lot of time in these trials. So our goal was to figure out when every plot, each of those 12 plots, every plot reached a key growth stage. The key growth stages of interest for us were emergence, first week of square, first week of flower, cutout, first week of cracked bowl, 60% open bowl. And I put the definitions up there because I think it's important. Sometimes we talk about early bloom and sometimes we talk about first flower. What I mean when I say first week of flower, and that is the date at which 50% of 10 consecutive plants have a flower. That's not when that one plant on the turn row put a flower on. We're talking about when that field enters that growth stage. And that was important. It took us a lot of time to capture that data. Most of the time we had individuals out in the field at least twice a week, if not more frequently than that. Spent a lot of time developing a data record-keeping process that would allow us to predict. Let's say we did miss that growth stage. We wanted to have some data before that plot reached the growth stage, and we wanted to have some data after. So we had some confidence in the date at which we reached each of those growth stages in each of those plots. And if we did miss it, let's say we were looking for the square stage, hopefully we would have data 38 days after planting before those plots reached that growth stage, some data while they had just broke, and then some data after. And that allowed us to have, again, tremendous amount of confidence that this is when we're actually reaching those growth stages. Tremendous amount of data. So each one of these lines is going to represent one variety observation at a given location. And this is just the 18 data. If you look, we got quite a range. We're looking at days after planting. I've got emergent, square, flower, cutout, cracked, 60% open. Got a lot of variation around cutout. And if you think about the one parameter in all of this, the one growth stage that's going to be most determined by your environment, that will be cutout, right? How long was our fruiting window? When did that fruiting window really shut down? Cutout, that's going to be the one that we would expect to have the most variability out of. Pretty tight from a square, flower, cracked, and 60% open standpoint. Very, 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 very good data. All right, now I want to talk about some of the results, and we'll start by looking at cultivars. So I've got the early variety here, mid-maturing variety, late maturing variety. These letters are going to indicate significance, right? And what we want to see, I'm on the northern edge of the belt. I want to get there quick, right? So I can't afford to be late to flower. If I don't have a flower by the 4th of July, it's going to be maybe a tough year. From an emergent standpoint, we did not see separation between the mid and the early. But from that point forward, it's a clear break. Delta Pine 1851, our full season variety, took longer to reach each key growth stage than our mid, and our mid took longer to reach each key growth stage than our early, right? So our early, it's getting to square first, getting to flower, cut out, crack, all the way to 60% open. That was interesting to me, that we saw that break that early on. The more important point to me, though, is look at the range here. Our 60% open for our earliest maturing variety, 2,480 heat units. Now, that's a pretty high number. We'll come back to that here in a minute. But the difference between our earliest maturing variety and one of the latest maturing varieties that I could actually get in 1851 was 85 heat units. That's not a big range, right? So, and I'll come back to this here in a little bit, but from a management standpoint, usually our later maturing varieties have a tendency to be a little bit higher yielding. You got a little bit stronger terminal. If I can manage that, if I can make that variety begin to fruit early, I can probably increase my yields, if not slightly, significantly. I was very, very surprised to see this tight of a range between my three cultivars, and significant. The one thing that was also interesting, and it kind of complicates variety selection, when we looked at, this is looking at DD60s accumulated since planting date. If we look at DD60s accumulated since the previous growth stage, that clear break, A, B, C, is not there. If you look, there's a couple stages where, between flower and cutout, Delta Pine 1646 takes more time than 1851. And 1646 and 1612 kind of flip back and forth a little bit. This is an indication to me that bowl period, the time it takes that flower to mature out to an open bowl, varies by variety, right? So there's an opportunity there to maybe we from a breeding standpoint, we start selecting varieties that have a little bit stronger terminal, would tend to try to be later, but we make sure we've got a very, very short bowl period there, could potentially increase our yields. It's a very, very interesting result there. One of my main take-homes, we compared our results with the results that have been collected. Anybody that's in cotton physiology typically have a Bible on your desk, the Mauney Blue Physiology Cotton Book. This is what they published. This would have been in the mid-'80s. This is the range of heat units that they published in the 80s. We've got Oosterhouse in 90, Wright out of Florida, Albers out of Missouri, Hutmaker in California. This is a little bit of an anomaly. Bange just published some results out of Australia, and I'll come back to him. If you look at our results compared to everybody else that's published up to this point, beginning at emergence, we're kind of right there in the heart of what Mauney published, but we are requiring more heat units than anybody else, and that trend holds all the way through the rest of these. From a square standpoint, it took us over 140 more heat units than the max range Mauney published. From a flower standpoint, look, we're right there at the upper threshold, but we're requiring almost 200, 300 heat units more than Oosterhouse, Wright, Albers, and Hutmaker. Continues through cutout, crack bowl, and another take home I want to make here. When we look at 60% open, our range here from cracked bowl, we're 200 above the range. When we move to 60% open, we fall very, very low in that range. So we're moving faster from cracked to 60% open than previously published. I mentioned the Bange results, and the reason that these are really interesting to me, our results are, it looks like we're taking a lot of heat units to reach these key growth stages. Bange just published, and he forwarded me the publication right as soon as he got it submitted. He said, hey, are you seeing the same things I'm seeing? We're taking way more heat units to get to a key growth stage than I would have expected based on previous publications. Our results are right in line with it, right? So it looks like all of our cultivars, either we're accumulating more heat units earlier in the year. I think part of that may be true, but we're also requiring more heat units to get to those key growth stages. All right, so this is going to change the way I manage that crop. We also looked at optimizing our base temperature, and I'm not going to spend a lot of time going through all of these results. We did find some numbers. From an emergent standpoint, our base looked to be best at about 72. We dropped into the low 50s when we're trying to predict square and flower, increased to about 68 when we get to cutout. At cracked, it's 52, and at 60% open, it's 64. The take home here is when we use those new base temperatures to calculate, to predict growth stages, we didn't really increase the strength of the predictions very much at all. So we added a lot of computational a lot of computational power and difficulty in changing these, but we didn't really benefit ourselves at all in predicting those growth stages. We also looked at including an upper cap, and the results were very, very similar. With the exception of emergence, most of the time they were above 86 degrees, low 90s, square at 100, cut out at 92, crack 94, 60% open 92. Same result though. When we applied that upper threshold, we didn't really strengthen our ability to predict growth stages. We additionally, and the one thing I felt like, man, solar radiation's got to be the one parameter that's going to really help us. It should really make a difference. Our climatologist forwarded this graph. This is heat units, and this is going to be solar radiation. This is not a perfect relationship, but there's a strong correlation there, a trend to where when we have additional heat units, we typically have more solar radiation. The sun's shining when it's hot. And because of that, we did not have very much of an increase in the ability to predict growth stages when we added that solar radiation parameter. So, on the refinement, I clearly think that we need to change the guidelines. We are seeing a significant shift. It takes more heat units to get to all of the key growth stages with the exception of that 60% open stage. Do we need to revamp the calculation? Should we look at moving the base temperature, upper threshold, and solar radiation, or varying these through the year? Based on our results, that does not look like it needs to occur. We're going to get these published immediately. I've got a manuscript that we're going to get to the specialist before Beltwide. But at this point, I have confidence in that DD60 calculation. It's not perfect, right? There's a lot of other parameters that can influence rate of growth, but I have confidence that we don't need to look at 58 or adding solar radiation. For what we're doing, 60 is going to work pretty well. Our next research steps, though, and this is really where I'm excited, I think there is a significant opportunity here to consider the differences in bulb period that we are observing by cultivar. And we've got a strong data set now to suggest that they exist, and I think it could be selected for from a breeding program. Now, I opened and talked a little bit about where I'm from in Tennessee. The take-homes that I give from this presentation to my growers, number one, our later maturing varieties are typically outperforming our early maturing cultivars. This aggressive PGR management for us is relatively easy. Most of the time, early in the year, we're going to have sufficient rainfall. We're going to have a strong terminal. We've got to make sure that we get light penetration down to those low subtending leaves to retain that low fruit. If you don't have that rainfall, aggressive PGR management early in the year could obviously hurt you. Keep that in mind. But if you're trying to break a yield goal and you have sufficient water, I would really suggest, and we've seen over the past several years, a lot of my growers have moved from earlies to early mids to a pretty heavy blend of mid-maturing varieties. If you're looking for to break a yield goal, look at a variety with a little bit stronger terminal, a little bit later maturing. The other take-home, very, very important, is we need to stretch our last effective bloom date. For me in Tennessee, it's August 15th to August 22nd. That's the last flower that I'll expect to get into the basket. I don't think that's true anymore. I think now it may be the 25th, it may be the 2nd. We're not taking as many heat units to mature out those fruiting positions as we were 30 years ago. Finally, and this has been important, and I put this picture up. This freeze hit us on October the 12th. It's one of the earliest freezes that we've had in a number of years. We didn't get the heat units we needed late in the year. We managed for earliness. We still weren't able to get them. We were cutting bolls to time those harvest dates. You need to make sure you've got mature seed, but you've also got to watch the calendar. And we unfortunately, a few of us got bit this year. All we got to do is get that boll cracked right before we get that freeze. A few didn't, and they lost a considerable amount of fruit because of that. But the best way to time that defoliation, that harvest aid bowl opening, is going to be to cut those bowls. Because we have variation in bowl period, it's not as easy as it once was on a note above crack bowl of 4 or 5 to pull the trigger. Dr. Arnold, that's the last I've got. If there's a little bit of time for questions, I'd be more than happy.
Plenty of time, Dr. Ray. Got any questions for Tyson?
Yes, sir.
I'm kind of disappointed that some radiation is coming. How does the diurnal variation in temperature affect cotton? So like we'll have summers where we may drop to 65 degrees, ramp up to 110, and then one summer we may drop to 75, ramp up to 90. Does that have any effect on the calculation of those heat units as well as not dropping below the threshold? And if it doesn't, does it have an effect on the cotton plant?
It's a very
Summarize that somehow?
Yeah, sure. So the question was, the swing in temperatures, how would that influence plant growth from a max and min standpoint? I think the bigger factor there, most of the time when we have those big swings, we have low humidity versus high humidity. And humidity for us, high night temperatures with high humidity clearly hurts cotton, hurts retention, hurts bowl size. We're going to have fewer seed per bowl. The swing itself does not bother me if we have low humidity, and I really don't even care if we get above 95 degrees late in the afternoon. What concerns me more is that 80-degree night with high humidity. That typically is going to be what hurts pollination and negatively impacts the crop. Now, from a maturity standpoint, and I think maybe that's one of the bigger take-homes. We've got to have a certain level of temperature, but the plant is steadily moving towards that end goal. And I expected solar radiation would really influence that, delay or mature it, and it just didn't. It was shocking. A very, very surprising result. Thank you for the question. Yes, sir.
How much impact does that have versus that high nighttime temperature? Because it seems like here with the high nighttime temperature is often bigger than
That's a good question, and I don't know. It's difficult for me to answer that for Oklahoma. For us in the Mid-South, yeah, if we have high night temperatures, it is because we have high humidity. Those two things are, the lower the humidity in the evenings, the easier it is for that temperature to drop. So it's hard to separate them for me. Now, in your environment, that would, if that occurs, that would, I can't quite answer that. Good question. It's a good question.